All right, welcome back. So we're going to revisit substitution today, and we're going to sort of, get a little bit more familiarity with the basics, and then sort of talk about how we can deal with substitution, or maybe a shortcut when dealing with substitution if we have an integral that is a definite integral with bounds. So just to remind ourselves, integration by substitution relates to the chain rule for derivatives. So the chain rule for derivatives, the derivatives of a function of some inside function, is just the derivative of that outer function, leaving the inside function alone, times the derivative of that inner function. So the way that we sort of, when looking at an integral, the way that we consider substitution appropriately is we first spot our inside function. In this example, note that 3x to the fourth plus 1 is inside the square root function. And so the first thing we might do is let u equal the 3x to the fourth plus 1 so that we can sort of evaluate whether or not u equals 3 to the x to the fourth plus 1 is wise here. And then that comes to step 2. Does some constant multiple of the derivative of u appear within the integral? Well, taking a look at u here, excuse me, the derivative of u, if we compute this out, derivative of u is what, just 12x cubed. And if we want to, we could move that dx to the other side so that ultimately the expression that we have below harmonizes with the expression above, where u's are on one side and x's are on the other. And then what you notice is the derivative of u is essentially 12x cubed dx. Well, hey, do we have a 12x cubed dx in our original function? No, we don't, but we have a constant multiple of that, right? 2x cubed is just a constant multiple of 12x cubed. In fact, what constant multiple? Well, to get, since we want 2x cubed from this here, we want 2x cubed dx. How can we get 2x cubed dx? Well, for me, as I see it, we can just multiply by 1/6. So what we'll do is we'll take the left-hand side and multiply by 1/6. Take the right-hand side, multiply by 1/6. As long as we're doing the same thing to both sides, we'll get an equal statement back in return. And the equal statement we get back in return is that 1/6 du is equal to the 1/6 and the 12 multiplied to be exactly the 2 that we desired. And hey, now we've got the 2x cubed dx that we are sort of interested in. So the 2x cubed dx, which is hanging out within our original function, is going to be just a 1/6 du, and then the u is going to be within that square root. So piece it all together, and what do we get? I'm going to be pretty emphatic here and write x equals 1 to x equals 2 because our original function was in terms of x, so those bounds are also in terms of x. However, whenever we make the substitution in terms of u, the 2x cubed dx, as we saw before, is just 1/6 du. And then what about that square root that's downstairs? Well, we would have what? 1 over square root u for that. And then if we'd like to sort of evaluate this integral, it's probably going to be easier to look at this square root u as a fractional exponent. Probably easier to factor out that constant of 1/6. So we still bound between x equals 1 and x equals 2. Again, I'm being emphatic about the x's here because when we use substitution, we've changed a variable. And by changing a variable, we don't want to then fall into the trap of thinking the 1 and the 2 from the original integral were along the u-axis. No, the 1 and the 2 here are along the x-axis. We'll have to take that into account whenever we ultimately evaluate using the fundamental theorem. But here, let's see, the 1 over square root u is u to the minus 1/2. And then, sort of to polish this off here, let's see, the integral of that is not too bad. Increase the power by 1 using the power rule, you get u to the 1/2. Take the reciprocal of that and put it in front, so that would be 2u to the 1/2. So 2u to the 1/2. And this is between x equals 1 and x equals 2. And so if we want to, we could factor out that 2 as well. That would work perfectly fine. And so ultimately, we'd have 1/3 times u to the 1/2, if I could write, from x equals 1 to x equals 2. Again, being emphatic about the fact that the 1 and 2, our initial bounds, came from the x-axis and not the u-axis. So at this point, there's sort of two ways to proceed. So one, I'll sort of take the naive route, and then two, I'll take the slightly sharper route. So initially what we could do here is just take this u expression and replace u with 3x to the fourth plus 1. And we'd get 3x to the fourth plus 1 to the 1/2 power. And this is between now x equals 1 and x equals 2. I guess the x is more superfluous at this point because we've got everything back in terms of x, but so be it. Whenever we write this out, applying the fundamental theorem, remember every definite integral is just a net change of antiderivative values. And so putting this in, we'd have what? 3 times 2 to the fourth plus 1 square rooted minus 3 times 1 to the fourth plus 1 square rooted. And let's see, 2 to the fourth, 2 times itself 4 times is 16. 3 times 16 is 48. 48 plus 1 is 49. And then over here, we've got 3 times 1, because 1 to the fourth is just 1. 3 times 1 plus 1 is 4. So ultimately, we have 1/3 times, let's see, we've got 49 square rooted is 7. 4 square rooted is 2. Put it all together, we get 5/3. So that is resolution, 5/3, to our evaluation of our definite integral. That said, I will say, this sort of method of computation, in some sense, effectively involved one extra step that could have been avoided. And that is, hey, when we were here at the point where we had everything in terms of u, the expression there was actually pretty straightforward. What could be nice as an alternative route here would be, instead of using the bounds in terms of x, so that's essentially what we did over here. We used the bounds in terms of x. You'll see, we'll save ourselves one step. If we convert our bounds to be in terms of u. What do I mean by this? Well, hey, x equals 2 and x equals 1 can both be converted into u's because we have this expression that u equals 3x to the fourth plus 1. So if we take our bounds and we work them out, our bound of x equals 2 would correspond to u equals 3 times 2 to the fourth. This is actually something we saw in our previous computation, 3 times 2 to the fourth plus 1, which is 3 times 16 plus 1, which is 49. And then we also saw that for x equals 1, u equals 3 times 1 to the fourth plus 1 would be 3 times 1 plus 1, which is 4. Now, if we leverage this in our computation, over on the other side, we could then just say u to the 1/2 from, well, I tell you what, I might run out of space if I do that, so let me do it over here, down here. Let's see, u to the 1/2 from u equals 4 to u equals 49. And now everything works out really nicely, right? Because we just have 1/3 times 7 minus 2, because we're taking the square root of 49 and the square root of 4 within our antiderivative, which ultimately comes out to be 5/3 again. So, like, as you'll see, well, as you do see here, instead of sort of having the 3 lines of computation additionally, we had the 2 lines of computation. And I know you're saying, but, you know, yo, prof, over here, didn't we have to make these extra lines of computation as well? I suppose so. I will say this may not be the best example as to why using bounds in terms of u can be advantageous. When we get out to later methods of integration, we can sort of show more sophisticated examples where using this bounds in terms of u method will be advantageous. But even just looking in terms of the chunkiness of the computation, look how many more symbols we had to write in each line, whereas here each of the lines are sort of more in bite-sized chunks. So yes, we still had some work over here, but the work that we had to do was ultimately cleaner. So I would sort of, I'm making a sales pitch in some sense for using bounds in terms of u, but knowing full well that both of these methods, either going back to bounds in terms of x and rewriting our antiderivative function in terms of x, or skipping the step of writing our antiderivative in terms of x and instead just converting our bounds to u, both of these processes ultimately lead to the same result, which in this case I suppose is 5/3. But in general, when you have a function that utilizes integration by substitution with bounds, you sort of meet this dividing point at some point, And don't be surprised if you're tested on knowledge of this bounds in terms of u-business, again, because there will be instances in the future where this bounds in terms of u-business will be quite fruitful. But for now, we've at least gotten more experience with substitution in general, and specifically when evaluating via the fundamental theorem. And in class, certainly we'll see even more examples of this, because this is something that the best way to acclimate yourself is by sort of repeated practice.